now. Okay, and then let's share the screen so we can get going. Okay, so we were at this point where we were describing this new parameter, which might be spelled NU. It's the amount bound over the total, basically. So all the different forms bound over the total. Bound ligand per protein. Okay, and then we went on to describe fractional saturation, nu over n. When n equals 1, obviously these are equal to one another, and you could do this generally with some kind of a signal change. And so that's sort of where we were, I think, when we finished. The next slide was a blank slide the last time. Okay. So I usually do this full screen. Is that the best way for me to do this, full screen?
Yes, sir.
Dr. B.
I agree. I think that would be helpful.
Okay. Okay, and then I'll move this as need be, the pictures here in the corner, because you see them, right?
Yeah.
Okay, so what we're going to do is we're going to go through most of the rest of this chapter. We'll see how far we get. At the end, we'll discuss or begin to discuss applications to hemoglobin. There are 2 papers in the next folder out on Canvas that we're going to go over, and that undoubtedly will be next week. Okay. And I'll probably have some filler stuff next week that will expand on what we go over today. So what Van Holde does, sorry, let me grab my pen so I'm ready to write if I want to. What Van Holde does is he kind of walks you through simple cases. Okay, and he starts with what he calls the simplest case. I'm just making sure my pen works here. And the simplest case is a single site where the protein binds to a ligand to make a complex. And you can write down in the traditional way what an equilibrium constant is. So this is association constant. The brackets mean concentrations. Generally speaking, it means molar for our purposes. If we change units, we'll tell you so. Generally, the conversion is a weight concentration versus a molar concentration. Those are usually the conversions that we make. And then he simply mentions that it's sometimes convenient to write dissociation constants down. And so it's essentially the inverse. And so the K dissociation constant is 1 over the K association constant. And notice this is a bolder form. So it's just 1 over the equation up above. Okay. So the units of K are generally something to the -1. So this is usually molar. Yeah, that's ugly. To the -1. And if you can see why that is, it's molar above molar times molar. So you end up with molar to the -1. All right. Down below, the units for dissociation constant are usually molar, because it's molar times molar divided by molar. And so it leaves 1 molar. So you generally report equal association constants. So 1 times 10 to the 7th, for example, mole to the -1. But you then usually report dissociation constants in terms of a unit of concentration. So the equivalent of this would be 0.1 micromolar. Okay, and so that makes this sort of easy, and you're familiar with this. And so in principle, you could do it either way. At the very end, if we get to it today, we'll derive Henderson-Hasselbalch in a slightly different way. And Henderson-Hasselbalch proton dissociations, or the equation is in fact a dissociation. So proton binding is usually described as dissociation constants. Okay, and in this particular case, then you can express this new parameter in terms of the concentration of bound ligand. The only form is Pa, and so that's expressed in the numerator, divided by the total concentration of protein, which is the sum of P and Pa. Okay, so the unligated form or the unbound form plus the bound form or the ligated form. All right. And then if you substitute Pa equals K times P times A, this comes from the previous, this previous where you bring the P and the A to the left, and then you substitute for PA. Okay, so when you do that, both in the numerator and in the denominator, so you substitute PA into this equation, you have P in all three terms, so the P's can all cancel. Okay. Does it? I don't know that it helps you. Maybe it does help you. For me to do this and this and this. And so you end up with K times A over 1 plus Ka. Okay. So notice from two definitions, this definition here and this definition here, essentially this single reaction, we have derived an equation, and this is what I meant when I said in my email that you derive an equation from sort of simple assumptions for K times A over 1 plus Ka. All right, and so this is a simple equation for the parameter nu, fraction bound, and over here it's plotted as fraction bound versus A, all right, the concentration. So this is the equation of a hyperbolic. It looks sort of like a Michaelis-Menten equation because the form of the equation is similar. You've probably already done that with John. And it has a asymptotic approach to some saturating amount. In this case, the saturating amount is 1 because there's only one binding site. Okay. The midpoint of the reaction occurs at 0.5 when half the sites are ligated. Okay, and that would correspond to the concentration where A is equal to 1 over K. Okay, so if A is 1 over K, then the numerator would be 1 and the denominator would be 2 because it's K times 1 over K. So if these are both 1 over K and 1 over K, then you would just end up with 1 over 1 plus 1. It'd be 50%. Okay, and so the midpoint is at the concentration of ligand when it is equal to 1 over the equilibrium constant. And we're expressing this right now as an association constant. So that's described in the legend down below here. Okay. And then just to be consistent for the moment, we then re-equate this with fractional saturation. Remember, it had to do with nu over n, and n here is equal to 1, and so it's the same equation, right? And then they state here what I just said, that this is an equation for a hyperbola, and it's clear that nu goes to 1 as A goes to a high concentration. They say infinity, but some exceedingly high concentration. The rule of thumb is to get 99% bound, you generally have to get 3 orders of magnitude above the K, okay, in terms of concentration. So to get some kind of a saturation. So infinity is a little, obviously a little bit out of reach. And then they rederive this or write it down as a dissociation constant, where you just substitute the 1 over bold k's to come up with a similar expression. It looks similar, except it's a over k plus a. Okay, where k here is a dissociation constant. Okay. So that's the simple definition of what a binding isotherm looks like if you have a ligand binding to a single site on a protein. For complete generality, we want to vary n. So we want to have more than one site. And when you have more than one site, the concentrations of bound ligand can be with one ligand bind, or 2 ligands bound, or 3 ligands bound. But the numerator is going to be the concentration of bound ligand. And so when it's a 1 ligand site, you multiply by 1. But when you have 2 ligands bound, you have to multiply the concentration of this by 2. 3 ligands bound, the concentration of 3. And so the summation is I equals 1 to n, where it's I times the concentration of Pa sub I. How much singly, doubly, triply ligated material do you have? This will give you the total concentration of ligand bound, okay? And that's explained in words below. And then the denominator is the concentration of macromolecule. So it's total bound ligand divided by total macromolecule. And so that would be the concentration of all of these forms, except there's only one P. So it would simply be the concentration of PAI, summed from I equals 0 to n, because it includes the term P when there's no ligand bound. So that has to be included in the sum. Okay, etc. And so the expression for nu becomes a numerator, sum I equals 1 to n, I times PAI, divided by sum from I equals 0 to n, excuse me, I didn't say that right. Numerator, I equals 1 to n, I times PAI. And the in the denominator, I equals 0 to n, the sum over PAI, where we're now summing over the total protein concentrations that are bound. Okay. What is then done is, in almost all textbooks or presentations that present this, is a derivation of what the Ks might look like, depending upon if you do each individual step or if you do overall binding constants. Okay, so overall binding constants on the right are written down. So if you have 2 ligands bound, you write down the overall constant. If you have n ligands down, you write down the overall constant. And you should see here that that means that it's going to be PA to the sub n divided by concentration of P divided by concentration of A raised to the nth power, because there are n ligands being bound. And like we had said before, this constant will have units of mole to the -1. This constant will have moles to the -2, because there's 3 concentration units in the denominator. And this will have concentration of equilibrium constant units of m raised to the n -1. Thank you. Leave that alone. Something like that. Okay. So if this was a 5, then this would have a units of -4. If this was a 10, this would have units of -9. Okay. On the left, we would write down stepwise binding. So you would first make PA, and then you would bound another ligand PA2 and another ligand and another ligand until you get PAN. Okay. And so you would always have on the left the form of the ligation one below what you're writing down. All right. And so then it'll be PA over P times A. It'll be a 2 over PA times A. It'll PAN over PAN minus 1 times A. So all of these will have units of mole to the minus 1. Okay, all the way down. Okay, and so they make a point here. All of these are in principle correct. Okay, you can write down stepwise binding, you can write down overall binding, and they all refer to one another or can be written in terms of one another. I'm going to show that on the next slide, I think, but that is shown here in his summary, that any ki is basically the sum of the products of all of the k's, small k's, stepwise leading up to kn. And so let me go ahead, I guess. Can be expressed in terms of formulation 1 is what I've recreated here. And so, for example, if I did K3, there would be K1, this is K1, and this is K2, and this is K3. And if you multiply them, the PA cancels, and the PA2 cancels, and you end up with PA3 over P times A cubed. Okay, and so whatever you choose, all of these would cancel out to give you the same value as the overall constant. Okay, and so that's what that expression down here means. All right. The other thing that he says here, yes?
I have a question that may not make much sense, but on formulation 2 on the bottom one, why is it m to the n minus 1 and not just n?
Here?
No, under formulation 2.
Well, there's, you mean the units?
Yes, sir.
It is n minus 1. It's a
No,
minus.
I don't know why it's not just n.
Because this concentration cancels this one. Oh, I'm sorry. You're probably right. I probably wrote that down wrong, didn't I? Thank you for paying attention. I think you're correct. I don't know what I was thinking about the left and not the right. You're right. This should be m to the minus n, because this 2 is what's left here. These cancel, gives you 2. These cancel, gives you n, m to the minus n. Ha, thank you. My mouth gets ahead of my brain sometimes. Okay, so the point that he's making down here is that physically, it's unlikely that n ligands bump into one another to make a complex, that there still is probably some path to get to this complex. And the path probably involves bimolecular steps. The path may in fact involve intermediates. Maybe those intermediates aren't populated. We'll come back to this a little bit conceptually later, but the part of the issue is what stabilizes the n ligands bound? Is it in fact the only species? Do all of these species exist? Probably they do. But just you can write down an equilibrium constant to define the overall equilibria, but that doesn't mean that all of these ligands have to come together. If this was a protein-protein interaction that made an enmer, there would probably be some kind of feature, for example, a ring of some kind that defined a maximum size, and the closure of the ring is what made it stable relative to everything else. But when it's just ligands with ligand binding sites, this probably just exists and it's in a path of a lot of other species. Consequently, often when we're analyzing data, we like to analyze data bimolecularly because it makes sense in a bimolecular way. And then the issue is, are the intermediates stable or not stable? Are there intermediates, etc.? Okay. So now when you write down the total ligand bound divided by the total protein, you then basically solve these similar equations for the what we had done above. You solve for the PAs in terms of the equilibrium constants, and so you bring the denominator terms to the left, and you substitute for PA, PA2, PAN. Okay, and when you do that, you end up with an I times KI, P times A raised to the ith power. Okay, and so we're substituting for this term out of that right-hand formulation 2 side. And so you still have the I here reflecting the fact that there are I ligands summed from I equals 1 to n. And then the denominator is still going to be without the I. It's still going to be summed from I equals 0 to n, K sub I, P, A, I raised to the P, concentration of P times concentration of A raised to the ith power. In this formulation, we have to define what K0 means, and we just set it to unity, okay? Because all it really refers to is no ligand bound. But for completion, we just give it some kind of a terminology, all right? Now, every single term will have a P, so all of the P's will cancel, just like they did below. And so we'll end up with this expression, this general expression, that historically is known as the Adair equation, that the new fraction bound ligand divided by protein is I Ki times A raised to the ith power divided by some I equals 0 to n Ki A raised to the ith power, okay? So this is general in the sense that we haven't put any restrictions on it. We've simply said that you can have as many as n ligands bound. When this was derived, Adair was working on hemoglobin, so he did it for four ligands because hemoglobin's a tetramer. But nonetheless, it's basically the general equation. There's no limitation on what K can be. Okay, the K1, the K2, the K3, the K4 in that particular case could be anything that they need to be. We're not saying anything about restricting them yet. Okay. And so generally speaking, you would have 4 binding sites or n binding sites, and this general equation would give you the shape of what the curve looks like. Okay, so again, it's nu versus A that we generally plot this as, and there'll be some shape to it. And the shape will generally give you some information about what's going on. Okay, and the maximum value up here will usually correspond to n, the number of total ligands. Depending on the magnitude of Ks, to get to n, that expression in the previous slide about going to infinity, you may have to go over a very, very broad range of concentrations to approach whatever the asymptote is up here. Okay, that comes up in a discussion below. All right, now what's said down below here is a determination of data, fitting data, and this was a problem that was exhibited with the hemoglobin data in the 1920s. There was they had a hard time fitting data in this way. You basically have 4 Ks in that particular case, and they can sort of be almost anything they want to be, and it's really difficult to nail them down. All right. And so there was a wide range of values, and it didn't really make a lot of sense to people in those days. They knew that there was something going on. They had no sense of the features that we're now going to introduce, but it just turned out to be difficult. So it's completely general, and that's the power of it. And so when you say the term a Dare equation, everyone knows in the field that it's the general starting point for describing binding data. And it's completely general for n greater than 1. Okay. So the first introduction then, or the first assumption is, rather than let the k's be anything, let's assume that all the sites are equivalent and independent. Okay, so the binding constants, the sites are equivalent. In other words, the ligand and the sites have equivalent molecular structures, and they're independent, meaning that there's no cooperativity, which we haven't even begun to define yet, between the sites. The binding of one site does not affect the binding of another site. So the other way we describe this is that the binding is non-cooperative. Okay. And then this is the important point now that comes up. At first glance, it might seem that this simply means that all of the k sub i's in formulation 1 are equal. However, this is not strictly speaking true. Okay, and the reason for this comes up here in this explanation. When you write down ki, large K, formulation 2, and you say that there are I ligands bound, okay, to the protein, or if you write it down as individual Ks, where it's something PAI going, or something PAI minus 1 going to PAI. The point is that there are lots of different PAIs or lots of different PAI minus 1s. There's a whole class of macromolecules with ligand bind that can be represented by PAI or PAI minus 1. So that's shown down below. If you have a tetramer, which they're representing here is alpha, beta, gamma, delta, and you start filling sites with 2 ligands bound, how many different ways are there to fill sites with 2 ligands bound? So this gets back to the expression that I introduced to you before, the count the ways expression, 4 factorial over 4 minus 2 factorial over 2 factorial. So this says, if you do the math, that there are 6 total forms possible. Here are 4 of them. Okay, so it's alpha beta or alpha gamma or alpha delta or beta gamma. Those would be 2 of them. Excuse me, those would be 4 of them. Notice there are only 2 across here. Another way to represent this would be to have 2 across this way in this funny tetramer, right? So if you did it this way, it would be one of the other forms. And then notice it's these 2, these 2, these 2. Okay, so what's not represented there? All right, and so it's going to be the 2 on the left here, right? So it'd be these 2 and these 2 represented as the 6th form. All right, and so the point is that when you think about concentrations and binding constants, you can make this form and this form and this form and this form and this all at the same time. So there's actually 6 different forms that can be present in solution and are present in solution all at the same time. Okay, so the overall binding constant has to be corrected for the fact that there are different ways of making it. different populations that exist at the same time. So when you write down the equilibrium constant, you have to take into account the fact that there are multiple concentrations that exist. And the way you determine how many different forms there are for any ligation state is this equation, all right, where it's the n factorial over n minus I over I factorial. So in this case, it's reflecting the number of sites, the number of ligands. So if we have 4 sites and we have 2 ligands, this is what you get. Okay, and that's 6. But if you have 4 sites and you have 1 ligand, okay, then this will be 4. And you can do the math, 1 ligand, write that. Remember what we did before. 1, 4, 6, 4, 1. This 6 sites with 6 forms with 2, 4 forms with 1, only 1 form with none, 4 forms with 3, which is another way of saying 3 empty sites, or 1 form with 4. So these are the coefficients of the binomial. These are the coefficients in the Pascal's triangle. These are the coefficients now that we have to take into account when thinking about the binding constants, all right? So the difference here is the terminology macroscopic versus microscopic. The microscopic constants reflect the difference between one binding site or one arrangement going to another arrangement, but only one particular site being ligated to create another particular arrangement. So how many total ligands are bound? What are the K's and the I's here? So it's the equilibrium constant, microscopic, or formulation 1K, where we're going from I minus 1 to I, but it's a particular arrangement. It's a particular conformation going from something to one of these forms, and every single pathway is represented and has to be accounted for, okay? The macroscopic binding constants multiply all of these different isomers, and I haven't used that term yet, but all of these are isomers of the same 2 sites bound. Okay, and so the macroscopic binding constant reflects all of the isomers. The microscopic binding constants reflect individual isomers and transitions between isomers. So what this means is that when you write down this equilibria and you have this conversion, it's an equilibrium constant where we have overall binding constants reflecting PAI, but there's an individual K that has to be accounted for the overall process, and that has to basically be corrected by this n choose K or n choose I parameter. There are multiple ways of doing this, and so you have to take into account all of those different ways of doing it. They have to be included in the overall expression, okay? And that's what this KI term ends up being. You have to include it so that it doesn't have this individual isomer inclusion. It reflects all of them at the same time. And I'm simply reading the text here, which probably says this better than I just explained it. So what this means is, and so this is a depiction of that, and I knew this when I was saying it. When you bind one site, you can bind any 4 to the first site. That's why there are 4 available sites here. There's only one site, one state, one microstate with none. And then you go to a particular isomer, which then allows another form to bind, which then allows another form to bind. But notice, once you're here, you can go to a number of different pathways. So instead of filling this site, you could have filled that site, or you could have filled that site. Okay, and those would represent different paths. You're here and you're going to fill this third site, but you could have filled this site. Okay, and so this is the point, that there are 6 forms of this and 4 forms of this and 1 form of this, and the pathway is complicated. But because the pathway is complicated, all it means is that the first ligand binding is K, but there are 4 ways of doing it. So you have to multiply by this factor of 4 to account for the 4 different species that exist in solution. Or there are 6 different forms here or 4 different forms here. And so in terms of the equation, we have to add this particular term. So remember up above, we had an equation, I big K, A raised to the I power. Now we have I, K raised to the I power, because each addition is multiplied together. They're all equivalent, so they all have equivalent microscopic states, K, or microscopic binding constants. But there are multiple ways of doing it, and you have to take all of those into account. Okay, and so for 1, this will be 1. For 2, this will be 4. For 0, this will be 1. For 1 site bound, this will be 4. For 2 sites bound, this will be 6, etc. And so this will correct for the total number of ligands bound, and this will correct for the total concentration of protein. All right. And so the denominator, and so this is the general expression. All right. So this is where things get a little complicated in the derivations that we're going through. We now have this overall expression. It's essentially still the Adair equation, but it's for all equivalent and independent sites. And now we're expressing it in terms of microscopic binding constants. So remember, the Ki is now equal to multiple Ks, right? So if this, whatever that I is, because you have to multiply each individual step out. And so that's why we end up with a K raised to the ith power here in the numerator and the denominator. Now we want to simplify this. Okay. So it turns out that the denominator is nothing but the binomial expression 1 plus Ka raised to the nth power. Okay. And this is what you would get for any individual term if you added this out. It includes the 0th term. Okay. And you can substitute this for the denominator. The numerator doesn't start at 0, it starts at 1. And so what he derives here in a couple of steps is the fact that if you rewrite this equation as an n-1 instead of n, and then you can redefine the range. n-1 here turns this term at the bottom into a 0, and you'll get n-1 factorial over n-1 minus I, and then I factorial. Okay, so you'll get this funny expression that you've rewritten, and then he makes this simple substitution, and he calls it something else. In the text, he explains that it's something else. Do I have that on the last page? I think I've missed some of the definition, some of the text. You can see that in the document, where he's redefined the indices, and he basically creates this new indices from this expression, where he's now redefining this as n factorial I plus 1. He's redefining I as I plus 1. And when you do this, you lose a term, or maybe you gain a term. You gain a term because he's added I plus 1. And we now end up with a Ki plus 1, Ai plus 1. And so he divides by Ka. He divides by an n. So you basically have added an n and subtracted an n, or divided by an n. You've added a k, you've divided by a k, you've added an a, you divided by an a. And then this is where he then redefines these expressions. He puts in, I think he puts in a j. And he redefines it so that the expression in the numerator ends up being written as an nka times 1 plus ka to the n minus 1. So look at that carefully and make sure that you can sort of figure that out. All right. Does that sort of make sense? And by redefining it, it then allows the 1 plus ka to the n minus 1 to cancel the 1 plus ka to the n. It leaves behind. So this whole thing at the top cancels, this cancels, and it leaves behind 1 plus ka. So the whole expression then ends up being nu is equal to nk times a over 1 plus ka. This looks exactly like the expression up above, except there's an n number of sites. So it's the inclusion of n that is different here. It actually will give you the intrinsic binding constant, even though you've accounted for all of the different forms up above. Okay, and so this type of analysis will work and give you the right value. Okay, so we've redefined the binding curve for n sites, all sites equivalent and independent. Okay, if you then divide by n, in this case, all you're doing is bringing n to the left, then you'll get fractional saturation, and it can be expressed as ka over 1 plus ka. It looks similar, except now the maximum number of sites will be expressed as 1 to 100%, or 0 to 1, or something like that. Okay. So this becomes another way. This form and this form simply become other ways of arranging the binding data so you can extract information. Now, this next section is generally fallen out of favor in a lot of the analysis of data, because we now have computers and we can fit data with computer analysis. But initially, we were fitting data by plotting it on graph paper and then trying to learn something about the data on graph paper. So there are many ways of manipulating these simple equations to potentially extract information. Okay, and so one of the ways of doing this is to simply turn the equation upside down. Okay, so if you simply take this equation at the top, okay, and you invert it, you get 1 over v, and this becomes 1 over nka plus 1 over, does that become 1 over n? Yeah, it becomes 1 over n. Right. Okay, and then you rewrite that here. You basically do what we would call in enzymology a reciprocal plot, and you plot 1 over v versus 1 over equals 1 over n plus 1 over nka. So the intercept gives you n, and the slope gives you this nk. Okay, and so it's a way of approximating the information. All right, so that's one way of plotting the data, and that's shown here as a 1 over nu versus a 1 over a plot. You now have two different versions. You have the chapter 15 that I gave you, a PDF, and you have the book that I gave you, which is actually chapter 14. And the figures in the book are slightly different, meaning they put error bars on the data to show you something about what the analysis really involves. Okay, it's the same plot, it's the same data, but it has error bars in it. But that's a double reciprocal plot. Another way of plotting the data I'm sorry, let me go back. This form of the equation, nu versus A, would look like this. Okay, so this is the hyperbolic equation, and this is what the hyperbolic equation looks like. This is from chapter 14 with error bars. You can see if there were 4 sites, it would approach 4 sites at really high concentrations. Okay, this is the double reciprocal form. Another way of plotting the data is to create something called a Scatchard plot. Okay, so if you rearrange this data, so what you basically have to do is multiply through by 1 plus Ka, and then rearrange the data so that you have nu over A is equal to Nk minus nu K. Okay, if you plot this versus nu, you will get something called a Scatchard plot, developed by obviously somebody named Scatchard. And it will have a slope of minus K, and it will have an intercept it will end up having an intercept of N. Okay, so it will give you information about the binding from the plot that way, and that's shown here. So this is a Scatchard plot, nu over A versus nu. The slope will give you information about K. The intercept on the x-axis will give you information about N. And you can see in this case, it's a 4-site situation. Here's the same data plotted in the other chapter with error bars. So this was a version of the book that came out, another edition, where they made the data a little more realistic, to showing you that the errors propagate in a way so it gets much worse at really high nu values. Okay, so that's another way of plotting the data. You can plot it as a straight hyperbolic. You can plot it as an inverse 1 over a double reciprocal. You can plot it as a Scatchard plot. And all we're doing is we're manipulating the data. Okay, if you rearrange this equation here as nu over A, let's do the whole thing first. Where's my cursor? There it is, over A. And we make this K times N minus nu. And then bring the N minus nu to the left and the A to the right. It will become nu over N minus nu is equal to K times A. Okay, so this is another form of the plot. And the form that you really want is the logarithm of this, where you take the log of nu over N minus nu, and then the log of a product is the sum of the logs, so it's the log of K plus the log of A. Okay, so this type of a plot, which is shown here at the bottom on the left and on the right. Okay, this is known as a hill plot down here. Okay, this is a log scale. They don't say log here. You can see it goes from 0.1 to 1 to 10. And this is a log scale. It goes from 0.1 to 1 to 10. So it's a log-log plot. All right, and it gives you information about both the intercept, the N value, and the affinity. Okay, so if we go back, we're plotting it versus A, and we're getting an intercept of K. Notice the slope here is 1. It's not written down because it's 1. Because right now what we're writing down is the binding constant. This is the equation for N, but in this initial form, we're writing this down as 1 binding site, okay, in this particular form. It writes it down generally as N, but you should realize something about this right at this point. To plot this data, you need to know N, because you can't create nu over n minus nu without knowing what n is. So you sort of have to know n to start out, to make this kind of a plot. Okay, that's sort of a deficiency in the data that you have initially. You sort of have to know n to convert this to something. Okay. So if I wanted to, let me do it down here. The log of k plus the log of a. All right. Remember, theta is nu over n. So if I multiplied and divided by n here, then I would get the log of nu over n divided by n over n minus nu over n. And that would end up being the log of theta over 1 minus theta, fractional saturation. And that will be the log of k plus the log of a. Okay, so if this nu is expressed as numbers of sites bound, the theta is fractional saturation. You could express it as 0 to 1, 0 to 100%, something like that, something in the right units so that this makes sense. All right. Notice half saturation still means the same thing. Okay, it's 0.5 over 0.5, the log of 5, and that would give you some information about what the magnitude of k is at the half saturation point. So that's another way of expressing a hill plot. We did this in Med Biochem when we were constantly talking about this, and I sort of just expressed things in that presentation as fractional saturation. And I probably went the other way. It probably told you that that's 4. Okay, so we've already done this once before in introducing the idea that what if there are multiple kinds of sites? They're independent, but they don't actually have the same binding constant. Okay, what happens then? Well, then the nu is the sum over multiple nus, where the S represents the different classes. Okay, and in general, each one of these can be written down in this same fractional saturation form, NS, KS, A over 1 plus KSA, but then you have to sum over all of the different classes of sites. S equals 1 to, notice now we're going to capital N for different classes of sites. Okay, so you could have high affinity numbers of sites and low affinity numbers of sites, where there are multiple high affinity and multiple low affinity. Okay, and they describe this down below as N1 strong sites, N2 weak sites, and the binding constant for the strong sites is bigger than the binding constant for the weak sites. So imagine a situation where you had 2 binding sites. You would then have 2 equations involving N1 hyperbolic, N2 hyperbolic curve. Okay, and so when you plot these by those various forms that I just showed you, you would learn something about both classes of sites, maybe. Okay, so if we just plotted it as a straight binding curve, nu over A, here he's representing 2 different situations where, imagine it's the binding constants are the same. So that's really 1 class of sites. It would just look like a normal saturation binding curve that approaches 8. But imagine that K is 10 to the 6th and K2 is 10, K1 is 10 to the 6th, K2 is 10 to the 5th. Then the curve would look different. It would approach n equals 4 for the first binding constant, but then there would be a more gradual, weaker binding event. And so it would have this sort of extended form that by eye is a little bit difficult to sort out. And then if they differed by 3 orders of magnitude, then you could clearly see that there's something happening early and then there's something happening later, and they're spread out by an awful lot. The first binding constant might actually be 4, and you can sort of pick that out. You can't really pick out where this is going. Okay, you're a long way away from 10 to the third. You're going to have to get out way out here into the hundreds and thousands to be able to approach what the maximum binding constant is. And so this becomes a difficult problem. You know there are multiple sites, you know there are different affinities, but analyzing it becomes different and challenging. Sorting these out might also be a little bit challenging by this method of binding or this method of analysis. Okay, and then there's a similar plot in the other chapter that shows different kinds of features. So A is equal binding constants, B is they are the same, but they're weaker. So you can see how it shifts and it's weaker. C is 10 to the 5th and 10 to the 6th. So it's similar to the one that I just showed you. And then D is 10 to the 3rd and 10 to the 6th. And are they plotting this over the same scale? He's plotting it to the same scale. He's going out to 60 here. The curve looks very different. This curve versus this curve looks very different. So there's something else different about this that I don't see. 10 to the 6th, 10 to the 3rd. In any event, it's quite clear that D or the previous one, it makes the weak sites difficult to analyze. Okay. This is a Scatchard plot. Okay. And this is one of the features of Scatchard plots that make it attractive in principle. If the Ks are both high affinity, then you can see that there's this long slope that points right at n equals 8. So it gives you the number of binding sites. For the second one, remember, they were only off by an order of magnitude. So there's an initial and then a higher order that approaches 8 if you go out high enough in concentration to be able to see that. Okay. And then when they differ by a dramatic amount, the high affinity site reveals itself, and then the low affinity sites, and remember, there are still 4 low affinity sites in this example, you don't even see them. You're never going to see them by this technique because you can't really go out high enough. It becomes experimentally very difficult, or by analysis, very difficult to see these low affinity binding sites. Okay. But in principle, you can see what the advantages might be. The slopes still give you the K in principle, but you basically have to peel it apart a little bit because the slope is complicated. It's the slope of the high affinity and the low affinity, and you have to sort of peel them apart. You have to basically have 2 different curves that sum to this curve. And so it makes the analysis really sort of complicated. This is why I say we generally don't do stuff this way any longer. We basically do it by computer analysis. The fourth way to do this is the hill plot. And so here's the log nu over 1 minus nu versus A. Okay. And A is for, this is for the same examples where you can see the affinity of the high affinity site and the low affinity site, and then the same high affinity site, but extremely low affinity sites. Okay. So this becomes a little bit easier to see. Maybe you can see that there's an inflection here. You notice that the slopes all in principle have the same slopes here. All right. But the way of sort of dissecting out what's going on is a little bit easier to see. Now, this is shown over here on the right out of the book, and he simply plots it. He simply plots it as high affinity, low affinity, and this downward inflection. Okay, this downward inflection that gives you the fact that there are two classes of sites, high affinity sites and low affinity sites. We're going to talk about this in a little more detail in a second, and I'll come back to this to make sure you understand what we're doing. Okay. So he then migrates, and this is all one big section in the book. He then migrates to what cooperativity would look like. All right. So non-cooperative is the middle curve. Negative cooperativity means that it comes up, but then it falls off. So it's less binding per ligand with negatively cooperative. And then the positive cooperativity is the thing that gives you this sigmoidal binding shape. So again, we're talking about 4 sites. The sigmoidal shape is recognizable to you as positive cooperativity. The simple binding isotherm may be obvious to you. You're used to seeing this as a comparison of myoglobin and hemoglobin, but in this case, all of the Ks basically have the same binding affinity. I know that because half saturation here is 2, and so they all cross at the same place. So they all have approximately the same or exactly the same affinity, where the half saturation gives you the K. Okay. One of them is non-cooperative, one of them is positive, one of them is negative. And so the question here is, what do we do to analyze this? What do our binding curves look like? Okay. Let me come back to this. I had moved this around in the A is non-cooperative, so it's analogous to what we were describing up above. We're depending upon the ligand concentration, all of the different forms will be populated. B is negatively cooperative, so it won't ever saturate because higher forms are suppressed, and you mostly have the lower ligated forms. And then the cooperative forms tend to push towards the high saturation forms. Okay, and so these are sort of saturation or distribution curves showing you what things look like. We'll come back to that, I think, when we've discussed this a little more. So this text, like most texts, describes how you interpret data. And this is two sections. Both of chapter 15 and 14 have this same sort of summary, but there's an expansion in one of them, and so I'm giving you that. So this is interpretation of a hill plot. Okay, and so in the text, it describes how you interpret data from a hill plot. If a straight line with slope unity is found over the whole range, the binding is non-cooperative and the sites are equivalent. Okay, so that's in one of the plots, this one right here. Okay, if the curve has a slope greater than unity in some region, then the binding must be positively cooperative. Okay, and this doesn't show that yet. Okay, so that would be a situation where the data curves upwards like this. And if the curve has a slope less than 0, or excuse me, less than unity, the macromolecule either has more than one classes of sites or the binding is negatively cooperative. The binding, the section down below says the same thing. And all it says, what's added on here, it's impossible to distinguish between negatively cooperative and multiple classes of sites. Okay. So this is a, Yes,
So here the unity means 1.
1. It means a
That's
slope of
okay.
1. That's
Okay.
exactly right.
Thank
Okay.
you.
Okay. So to begin the quantitative way of thinking about this, and this is all sort of an introduction to how you would actually quantitatively determine this. This set of rules is sort of a way of thinking about what's happening with your data. In principle, you can see this in all of the different plots. All of the different plots will look like, will have a certain feature that will allow you to interpret them. Okay, but we generally write this down specifically for hill plots because this is the preferred way of analyzing cooperativity. And so in principle, you can look at any one of these curves and sort this sort of stuff out. Is it non-cooperative? Is it negatively cooperative? Is it multiple classes? Those two are equivalent. Or is it cooperative? Okay, so that's a conceptual and that's a qualitative explanation. What we want is a quantitative explanation. All right. So to begin this process, we need to imagine a situation to help us understand what's going on. And the situation that he describes is what I'm going to write down as all or none. Either you have nothing bound or you have a maximum number of ligands bound. None of the intermediates exist. Okay, none of the intermediates exist. All of them are bound or nothing is bound. Sorry. Okay, so when you write down the fractional saturation or the new curve, the new equation, it's n times the concentration of PA to the n, sub n, divided by P plus PA to the n. So this is all of the ligated forms. There's only one form and there are n ligands bound. And all of the protein forms, no ligand, saturated. Okay. If you then substitute in the appropriate K that you would get the Kn because it's the total overall binding of n ligands. It's A raised to the n, and you get this Kn A raised to the n in the denominator. All right. And then if you rearrange this equation into a hill plot, you will get nu over n minus nu, the log of, is going to be equal to the log of Kn, and then you'll get n times the log of A. So you'll now get n, the number of sites, and that will be the slope of the line if you express the data in terms of this model. Okay, and so I think it's important to understand that what we're doing here is we're developing models to extract information out of the data, and then we're plotting the data to that model to see if we can get the information we need. I repeat to you, the slope is n, but to plot the data, you need to know n. Okay, so you sort of have to reconvert this to a theta over 1 minus theta. But to do that, you need to know n. What did you divide by to get n? There'll be a problem at the end in the assignment that confronts you with this problem. Okay, so this is the all or none situation. Okay, if you have intermediates, then you will have transitions between none bound and 1 and 2 and 3 and up to n. Okay, so it'll look more complicated. So here's a traditional way that you have seen data presented. This is not quite the myoglobin, but it's approximately the myoglobin situation. This is n ligands bound. You'll notice you can see it in the data that it's a non-cooperative binding curve. So it looks like a usual saturation curve that comes up to N. And then there's a sigmoidal curve that has that classic shape. So this is non-cooperative and this is cooperative. And remember I said you can tell that in the other different plots if they're presented correctly. All right. So just showing it this way, you can tell the difference between non-cooperative and cooperative. One of the things that you want to try to learn from this presentation in this chapter is how to interpret data. Okay. And when you plot data in certain ways, plucking out what the model is and what the interpretation is just from the shapes of the curves. This is what positive cooperativity looks like in a hill plot. It's log of nu over n minus nu versus log a. It starts out as a straight line down here. It transitions in the intermediate section, and then it becomes a straight line up here. The slope on the edges have a slope of 1. Okay. And the slope in the middle is what is called the hill coefficient. If this were perfect data, the slope here would be 4. But because you have intermediates, so as this plot over here suggests, the slope would be n. But if you have intermediates, you don't have 4 bound until way, way, way out here somewhere. And so what you get is some kind of an intermediate coupling between all of the different sites, and it generally is less than n. In the case of hemoglobin, it tends to be around 2.3 to 2.7, depending on the data set, the conditions, etc. Okay, and so it in principle gives you the number of sites, or it tells you approximately what the number of sites are, and you have to sort of extrapolate and guess from that moment on. But it's a way of getting the number of sites or an inference towards the number of sites. The shape of the hill plot is clear. This is cooperative. It starts out with low affinity and it goes to higher affinity. We are going to delve into a different model now, but our nomenclature is that down here we're in the T state, and up here, we're in the high affinity R state. So at low concentrations, this is the T state. At high concentrations, this is the R state. The concentration, remember, is down here. All right. The other way of thinking about that is the intercept. If this intercept here, if this corresponded to the 50% point, okay, where this curve crosses the intercept right here is the affinity of the T state, and it's at relatively high concentration. Where this curve crosses the R state, can you see that cursor moving around?
Yes.
Okay, that point is the affinity for the R state. It's at lower concentration. It's at higher affinity. Okay, so I'm describing this in terms of dissociation constants. So that's the crossover point that gives you the K. This intermediate value gives you the numbers of sites or the hill coefficient or inference about the numbers of sites. It's never the number of sites. It's always less than the number of sites. Okay. And so this is that all or none case that I showed up above. Did I show this twice? I did show it twice. Okay. And so it takes this simple form, and I've already pointed out to you the problem with n. Okay. So that's the general idea. This was all figured out. Hill was working on hemoglobin in the 1910s and 20s, okay? This was all figured out a long time ago. And so the hemoglobin people continued to think about this problem. Yeah, there are 4 sites. Hemoglobin's a tetramer. They sort of knew what a heme was. They knew that there were 4 sites. They could sort of see that in the hill plots, but they still didn't quite know what to do. They were still trying to fit it to the Adair equation, getting a distribution of Ks, similar to the distribution plot I showed up above for different ligated states, but they didn't quite know how to analyze the data. In the early mid-60s, Monod, Wyman, and Changeau, you may or may not know any of those names other than from this plot, from this historical form. I teach this in Med Biochem. You must have learned it in your own biochem class. Monod and Changeau were in Paris, and Jeffries Wyman went to visit them and worked with them for a long time. And they came up with this model. All right. Monod and Changeau were also working on gene expression at the time, and they're famous for a lot of the work that they did on gene expression and regulation of gene expression. So if you Googled them, you would find a lot of that work. And the model has become the MWC, Monod, Wyman, Changeau, or it's become what is called the concerted conformational transition. Where is it? Concerted conformational transition, so that the subunits in a multi-site protein convert between 2 forms. There's one form that is weak binding, and there's another form that is strong binding. And the forms have the general designation of T, the low affinity form, and their nomenclature, they called it tense. And the R, or high affinity form, in their nomenclature, they called it relaxed. Okay, and so there's this transition in the quaternary structure between the T and the R state. And either the tetramer is in the low affinity form or the tetramer is in the high affinity form. And the conversion from T to R is cooperative. Okay, so ligand binding converts T to R, but that conversion depends on the magnitude of the cooperativity. And so the model that they come up with is that there's an initial equilibrium between the T and the R form, and you can literally write down an equilibrium constant, which they called L, where it's the T divided by R is L, the equilibrium between the T state and the R state. So this is an equilibrium model involving conformational transitions. Okay. Around the same time, no, this is not, I'm jumping ahead in my head. I should not be jumping ahead. This is the idea from the book, the Van Holde book, that there were then 2 different conformations, low affinity, high affinity, T and R. The T state was low affinity, the R state was high affinity, so KR is bigger than KT. All right. So you have this equilibrium between states, and that equilibrium is shifted by ligand binding. And so in the low affinity form, ligand will bind with KT, and all forms in the T state will bind ligand with affinity KT. So notice, all sites express KT affinity in the T state, and all sites in the R state demonstrate KR affinity. Okay. So the concerted model is all of the tetramers are in the low affinity form, all of the tetramers are in the high affinity form, and the conversion happens between the oligomer states. All right. And so this is the basic information that you need to define the model. There's an equilibrium between quaternary structures, and there's a low affinity and a high affinity form. So we can immediately write down what the binding isotherm looks like. And recall the binding isotherm. Let me jump back here just to find it.
Hey, Dr. Correa,
Yes.
just a really quick curiosity question. How in 1910, 1920 did they know that hemoglobin had 4 binding sites, had an N of 4?
Osmotic pressure. They were doing osmotic pressure experiments. And then starting in the 20s, they were doing sedimentation experiments. So the
Okay, that one kind of makes sense to me.
Okay, so initially it was osmotic pressure,
Wow.
and then the sedimentation data showed that hemoglobin was a tetramer. So I said something at the beginning of the class about this. So that in the teens, we thought proteins were colloids. And we thought they were just these gamishes of things sticking to one another, okay, that they had no defined structure. The osmotic pressure began to say, no, 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 there's really a particular molecular weight here. They were still uncertain about interpreting it. And then the sedimentation data, which I'll show you in a few weeks, said, look at that. The hemoglobin tetramer is really just a tetramer. That's actually not true, but under the condition that they did the experiment, it was all tetramer. It's not just this blur of stuff. It's really a defined structure. So they got the molecular weight. They also, without necessarily realizing it in terms of nomenclature, they created the quaternary structure nomenclature. Okay.
That's fascinating. Thank you very much.
Okay, and so this is the general equation here for the binding site, all sites equivalent and independent. Okay, and so this is the form that we came up with initially. Now we're talking about cooperativity. And here we are way down here for the hemoglobin form of this equation. And notice it has a similar sort of structure. That equation up above came from substituting in values for the Ks in the As using one of the formulations for the Ks, okay? But now we have complexity. The complexity is that the ligated forms can be either to the T state or the R state. So you have 2 sums to deal with. I times RAI and I times TAI. And then down below in the denominator, you have R forms and T forms of the protein, and you have to account for all of them. So when you plug in now the same equations that we talked about, you have to put in this sort of N choose I. This is one way of expressing this nomenclature. Okay, so you have to plug in this nomenclature. For the RAI, you get K raised to the I times A raised to the I, and you multiply by I out here to account for the total number of ligands. And you have to put the same thing in the T state, where it's KT and KR in the appropriate place. And then in the denominator, you end up writing down the same equation, but without the I. It's just a concentration of the protein, not the ligand. You'll notice that the concentration the concentration involved an R term. Remember what we did up above is there was an R in the numerator and the denominator, and it canceled. And we can't do that now because it's an R term and a T term in the the numerator and the denominator. So they don't directly cancel. Okay, but otherwise everything is the same. If you go back and you just look at the left side, it looks the same. If you look at the right side, it looks the same. The problem is you need both terms. It's way more complicated, or it appears way more complicated. Yes? Okay. Now what you do is you substitute using an equilibrium expression, and you substitute T is equal to L times R. And I didn't say this up above. I must have skipped it. It doesn't say it here. I just didn't say it. And then we substitute a ratio. C is equal to KT over KR. Okay, remember KR is bigger than KT, high affinity, low affinity. So C must be less than 1. Okay, and so what we have here, the complexity is we have R and T. The complexity is we have KR and KT. And so we want to get rid of 2 of them. We want to get rid of T and we're going to get rid of KT. So when we make that substitution, okay, then suddenly KT becomes L times R. And so that T that was out here at the beginning is gotten rid of. And there's an R that's in here, but there's an R now in both numerator and denominator terms. And so the R's will cancel. And we won't have KR and KT, we'll have CKR. This substitution is made here, okay? And so you should try to make these simple substitutions here, here, and then cancel all the terms that you can. And this is the form of the equation that you'll get. All right. Notice that we have this n minus 1 and over n. And when it was simple, these would cancel and you would just get a 1 plus KRA in the denominator. That doesn't happen anymore because there's 2 terms. And this term involves the L and the C, the linkage between the T and the R conformation, the linkage between the KT and the KR affinities. All right. And so this would have reduced to NKA over 1 plus KA. It doesn't anymore because there's 2 of them and it's more complicated. All right. Now you can see what's coming. He says it in the book. This needs to be simplified in some way, shape, or form and converted to a hill plot, just like we did up above. Okay, you can convert this to a hill plot. There's a lot of algebra. I'm asking you to do it in the next assignment. And so you'll end up doing your best to kind of rearrange all of this stuff. And you'll find that you get nu over n minus nu is equal to this common term, KR times A. And then there'll be 2 terms here, one involving LC in the numerator and one involving L in the denominator. And then we'll have these 2 ratio terms involving essentially the same term raised to the n minus 1 power. You can't cancel them because there's a C here. It's 1 plus this expression. So these don't directly cancel at this point. Okay. This basically is the hill plot for hemoglobin tetramers or any ligand binding system that has N binding sites. Actually, when we derived this just now, we didn't specify what N is. I'm talking as though this is going to be hemoglobin. Okay. To make sense of this, you now have to begin making approximations. And so when you start with this particular form and you make an approximation as A goes to 0, okay, so just substitute A in here going to 0. This term and this term and this term and this term go away. And this expression will simplify to 1 plus LC and 1 plus L. The things that they were multiplied by go away because it's A goes to 0. Okay, and so it becomes a simpler form. If A goes to a really high concentration, then the term up above, A goes to a really high concentration, okay, then that becomes the dominant term. The 1 essentially drops out, okay, and then you can excuse me, I'm down here. I'm not up there. I'm down here. The A gets large relative to 1, and these terms then can be canceled. And what you are left with is a C raised to the n minus 1 power, C raised to the n minus 1 power. So this will end up being C to the n. Okay, and in the denominator, you'll get a C to the n minus 1 because there's no C out here. So as A goes to infinity, it will give you a different expression. All right. They're basically trying to break this down to help you understand how you might interpret this. Then they make further approximations in the discussion. If L is large, the T form is highly favored. So if L is large, the 1s go away. Okay, if the 1s go away, then the LCN and LCN minus 1 cancel. The L's cancel, and you end up with a C term. So that whole expression will be KRA times C, which is equal to KTA. And so under these conditions, and as A goes to 0, you will get KT. Okay, so stop for a second. I realize this is just a lot of math and confusing to you. Under these conditions, A goes to 0 and L is large. The slope of the line will be the affinity constant for KT. So if we go back to the plot that I had, as A goes to 0, going to the left, and T predominates, you'll get KT. It will be this part of the data set will give you KT. Okay. Alternatively, at low protein concentration, so as, excuse me, I'm mixing up here. Low, so this low A refers to this part. And then the next approximation is that if C is small, so remember C was, it was KT over KR. C is small, especially if N is large, then this will approximately become this expression. This will reduce to this expression. And at high concentrations, the plot will give you KR. Oh, sorry. Gotten ahead of myself. So the plot will give you KR. It was, I had to go back here. Up here. Okay, so if we extrapolate from those conditions, that will correspond to a slope for giving you KT. Okay, at high concentrations, the slope up here will extrapolate to KR. Okay, and so it's this part of the curve will give you the KR. It's this part of the curve will give you the KT. So he's trying to rationalize for you what the mathematics is showing you. Okay, that it initially gives you the KR value, and then it transitions with a Hill coefficient to a high affinity KR state. All right. Do you have, at this point, do you have any questions for me?
Dr. Correa, I have a question, but it might take up too much time because it's kind of hypothetical.
It's okay.
All right, so I don't know about my classmates, but my brain is kind of slipping out of gear sometimes with this because we keep talking about the data set and the manipulation of the data set. Could you give us like an example maybe of an experiment that would result in the type of data set that we could do these manipulations with?
You're going to get that in the homework, and we're going to do that when we talk and when we do that and talk about hemoglobin.
Okay, that's great. Thank you.
Okay. Anyone else? Okay. So I'll say more about this probably next week, because I think I'm going to have some filler that I want to have. Around the same time, actually a few years earlier, Koshland, Nemeth, and Filmer, it's now called the KNF model. The sequential model is the other word that is used, had a different model. And their model wasn't all or none, meaning T state, R state. Their model was a tertiary structure. So the Monod-Weinman-Changeau is essentially a quaternary structure model. You go from a low affinity quaternary structure to a high affinity quaternary structure. The other thing I didn't say about that model is that model only allowed positive cooperativity. The Koshland-Nemeth-Filmer model allowed negative cooperativity. But this model involves tertiary structure. So if a ligand binds, there's a local conformational change. And when a second ligand binds, there's a local conformational change, et cetera. And it can bind to the multiple sites, and you have the same pathway issues and the same N choose K sort of microstates that you have to deal with. But the transitions are more sequential and more gradual. And eventually you get to 4 sites bound and a total quaternary structure conformational problem. They fit the data equally well. I'll say more about why the data is more complicated. And so the book at this point transitions to hemoglobin. And it shows you the oxy-deoxy crystal structures. If you go back and you look at the hemoglobin lectures, the second hour of the hemoglobin lectures, we discussed this. The major conformational change that occurs upon oxygen binding, a rotation between dimers that we've discussed in the past. And these 2 slides are from my lecture before. And I'll say more about this next week. Up above is the Monod-Weinman-Changeau model. I think this figure originally was stolen out of Stryer or something. Here's the low affinity state. Here's the high affinity state. Notice the KT, the KR. They don't show you the equilibrium constant. What they're showing you is that the equilibrium shifts because of ligand binding, and it shifts from low affinity to high affinity form. 1 ligand bound, 2 ligands bound. Remember, this does not reflect the full complexity here because there are 4 forms with 1, there are 6 forms with 2, etc. But nonetheless, it's a depiction of the all or none sort of model. In this case, all or none doesn't refer to ligand binding, it refers to conformation. You're either in the low or high affinity quaternary structure and the ligands bind. And the pathway tends to be along this high affinity pathway down below. You will always have T-state forms. It will depend upon the magnitude of the equilibrium constants between them. All right. The sequential model says it's only tertiary, it's local tertiary, and it happens gradually along the path. Okay, and the affinities for each tertiary structure are essentially the same as you move along. Okay, the thing that happened in the field, and this is what we'll go into in more depth next week, is that the Akers lab discovered when they did certain kinds of experiments, and you and I will talk about those experiments next week, as long as the ligand stayed within a single dimer, you know, and I'm not telling you that now, we'll come back to this. Well, I did say that to you right here. This rotation here is dimer rotation. Okay, so there's an alpha beta structure, and they rotate relative to one another. Okay, and that's what leads to the T to R conformational change, what we will call the deoxy to oxy form. As long as the ligand was within a dimer, this is a sequential model. Once the ligand crosses the dimer interface, so imagine this one is in here, then the entire structure senses it and it transitions to a Monod-Wyman-Changeau model. And so this is what they called the hybrid model. It starts out sequential, but if you cross the interface, you get concerted all or none, Monod-Wyman-Changeau. So yes, there are tertiary conformational changes that occur. And yes, there are quaternary conformational transitions that occur. It depends upon the ligation state and where the ligands are in the conformation. All right, so we'll go into more detail about this next week. Although the book shows you some of the states. So you can imagine one ligand bound within a dimer. This is still in the T state because it only has one ligand. This state is still in the T state because it only has two ligands in the same dimer. All of these different forms have crossed the interface. These have transitioned now to the R state, as depicted by the square to the circle. And then all of these end up being in the R state. Okay. This is the kind of binding data that we can talk about and we will talk about next week. This is coming from one of those papers. Notice it's showing fractional saturation. It's showing oxygen concentration. Appreciate that this data has to be collected with a gas. So you have to know what the concentration, the partial pressure. This is plotted as molarity, but this is really initially done as partial pressure. These are binding curves, oxygen binding to hemoglobin. Okay, so here's a sigmoidal shape telling you it's cooperative. You can tell that by looking at it. What's varying here is down below, the hemoglobin concentration. They are varying the hemoglobin concentration. We'll recover that information later, but notice this goes from 40 nanomolar to, that's, what is that? That's 0.1 millimolar, that's 100 micromolar. Okay, you know that hemoglobin concentrations in cells, in red blood cells, is very high. We should actually do that the next time. We'll try to figure out exactly what the hemoglobin concentration in cells is relative to this. This is a test tube experiment, right? So if you go from high concentration, this is 0.1 micromolar. No, that's not 0.1 micromolar. It's 100 micromolar. 100 micromolar. It's 0.1 millimolar. 0.1 millimolar. And this is 40 nanomolar. Okay, and so what it's showing is that if you lower the concentration and you do the binding curve, the curve shifts from cooperative to non-cooperative. What this means is that tetramers are cooperative, dimers are non-cooperative. Remember I said they rotate relative to one another. Well, when they're free dimers, they are not contacting anything. They have no external signals from another molecule. So the curve shifts from cooperative to non-cooperative binding. And notice the affinity becomes much higher because it's the midpoint. Okay, the affinity becomes higher in the dimer form. So forming the tetramer creates this lower affinity form that transitions between a low and a high affinity quaternary structure. There's lots of stuff going on here, right? This is a depiction. Yeah, this is a depiction of the full complexity of this. You have a dimer tetramer equilibrium. You have an oxygen binding, 1 ligand, 2 ligands, 3 ligands, 4 ligands. The oxygen combined to dimers, the oxygen combined to tetramers. What they're doing is analyzing the data that I just showed you by analyzing every individual step. What's the equilibrium constant to make the tetramer? What's the equilibrium constant when it's ligated, doubly ligated, triply, etc.? How does the oxygen binding change in the tetramer and in the dimer? Notice the binding to the dimer is constant. It's not cooperative. So there's simply a fixed affinity. Whereas in the tetramer, the affinity gets tighter and tighter and tighter. These are expressed as log units, okay? So the affinity in terms of free energy, excuse me, these are expressed as free energies, gets tighter as you go down. This is going to take a lot more explanation. Let me finish with this one statement. Each one of these boxes is what's called a thermodynamic cycle. Okay, so each box is a thermodynamic cycle. Notice minus 14.3 and minus 5.4, that's 19.6, 19.7, if I can do the math. 8.3 and 11.4 is 19.7. This sum and this sum are equal. And if you go around any one of these boxes, you will find that these two numbers, the 8.3 refers to each step. These two numbers add up. Remember what we said. Thermodynamics is a state function and the free energy is path independent. If you first dimerize to a tetramer and then bind a ligand, or if you bind a ligand and then tetramerize, you will get the same overall free energy. And that will be true of each one of these sums, okay? The cooperativity ends up coming in the cooperativity relative to the non-cooperative state. So this 0.8 corresponds to the difference between 9.1 and 8.3. This 1.6 corresponds to the difference between 6.7 and 8.3. So this is the cooperativity that shows up, the difference between non-cooperative and cooperative binding. All right, let me stop with that. So this data is coming out of these two papers that are posted in the next block. Let me stop sharing. And we're still recording. All right, so I know we just went over a lot. All right, we went from single site to multi-site. We then went to equivalent and non-cooperative, equivalent and independent. And then we started plotting data by different plots to get information about the numbers of sites and the equilibrium constants. We showed you a direct plot. We showed you a Scatchard plot. We showed you a double reciprocal plot. We showed you a hill plot. Okay. You're not used to this. Okay. I think this way. When people show me data, if you show it to me the way that I just showed it to you, I can interpret just by looking at the data. Independent, single site, multi-site, cooperative, anti-cooperative, etc. And you can tell that from the shapes of the curves. So I teach it the way that Van Holde sort of teaches it. And what that means is Here it gives you a conceptual grasp. And then there's this transition, excuse me, where we talk about how you interpret Hill coefficient data or Hill data. Okay. Single straight line, non-cooperative. Upward curvature, cooperative. Downward curvature, heterogeneous, multi-site, or negative cooperativity. There aren't a lot of negative cooperativity ligand binding data. There's some, but there's not many. And then we assigned it to, okay, now we're at the Hill coefficient phase of this. We're at the cooperative phase of this. How do we derive an equation for this? And so we derived Monod-Wyman-Changeau. That's a 1965 Journal of Molecular Biology paper. It's a quote unquote classic. It's a paper that everybody in biochemistry, everybody in quantitative biophysics should know about. The derivation of it is as directly as I showed you. It's really just manipulating the same math, lots of rearrangements, but it's introducing the same multiple microstates to simplify it. T state, R state forms, both in the numerator and in the denominator. And then it comes out with this really complicated looking equation that involves a quaternary equilibrium, L, T to R, or maybe it's R to T because L is T over R, and then C, the ratio of the equilibrium constants. And then it can be approximated or broken down into different phases of the curve. What we didn't get to yet was talking about the slope of the intercept in the middle, where you get the Hill coefficient. We'll sort of start again next time, and we'll repeat a lot of this stuff. Look at those two papers. Look at what he discusses in the book. He's basically stealing all of those figures, some of those figures from the Akers papers. So next time we'll talk about those two manuscripts and we'll go into experimental details. Okay. We're not ready for the next assignment yet because I think a lot of the questions in the next assignment come from those papers as well, or something more about the data. It'll come out of mostly the chapter that we just did. Okay, so I think assignment 6 had to do with the stuff that we were finishing last week. Am I right about that?
Yeah, and then you added only one question on assignment 6, I guess. It was assignment 5 and you added one more question, right? That's what I think. I might be wrong. Yeah.
The numbers on assignment 6 aren't all the same from assignment 5.
Yeah.
Is that your confusion?
Yeah, me and Sarah, we were a little confused because we thought the assignment 6 would be totally different than assignment 5.
But it
then-
comes from a different chapter, doesn't it?
Yeah, it said on assignment 6, it said it was a different chapter, but there's only a number 2. There's not like a 2.7, 2.2
Oh,
from that chapter. But
okay.
there are those numbers in the chapter that we did last week.
Yeah.
Yeah.
Okay, so we used last week's chapter for the first problem and then the new chapter for number 6. Is that right?
Yes.
Okay.
Yeah, and then assignment 7 is from what we are
Discussing now.
discussing now. Yeah.
Right.
yeah.
And so we're
okay.
not ready for that yet. So hold on a second. Let me.
Where did it go?
So chapter 2, thermo and biochemistry. So I'm going to share my screen again. That's this where you did this delta H minus delta E, delta S. And then down here, there was the helix random coil calculation.
Yeah.
And then there were the different supercoil twists. This is the one that I'm grading because most of you have turned in problem 5, assignment 5.
Yeah, yeah.
Okay, so it was 2-3, 2-5.
2-7. There was 2-10.
Was there another problem? Oh, it was the derivation. No, that was in the next one. Was it just those 3 problems? I think it was just those three problems. And then the other Van Holde chapter that says solutions of macromolecules. This also had a 2-3, a 2-5, a 2-7. So that's why the
Yeah.
numbers look similar.
No, actually, I think if you open the solution of macromolecules chapter,
I'm in, that's what this is. This is the
the
solution.
the question there, let me double check. I might be wrong.
Yeah, maybe we messed something up.
2 point. Okay, if you go to the question from that chapter, it does not list as 2.3 or 2.8. It's
Oh, it
1,
listed
2.
as 1, 2, 3. I'm sorry. You're right.
Yeah, that's where we were confused about the question.
Sorry.
So that means,
You were telling me there was a problem and I wasn't believing you.
okay, now it's clear. Okay, it's just,
So this should be, well,
yeah.
so this
Mhm.
should be problem 2, not 2.2.
Mm,
Well, it's chapter 2, problem 2. And so there's my confusion. So it should be problem 2. And that's what you're telling me. That's interesting. I've just copy pasted this from previous years.
yeah,
No,
that's
and
where
now
we
I
were
just-
checking at this chapter, and then the question were listed as 1, 2, 3, 4, and then we were confused with
Right, so it
Right.
should be 3, 5,
6, 7.
6, and 7.
Okay, that makes sense.
Is that clear?
Yeah,
Sorry.
it's clear with me.
So I'll repost this out there. And then I've added this practice of differentiation by making you do an exact differential for ideal gas and for non-ideal gas.
Yeah.
Any
So
more?
Dr. Correa, I have a question.
Yes,
On that 6th assignment, the one that you added at the bottom, that's your own problem. That's not from the book, or it is?
no, that's my own problem.
Okay.
But I sent you a PowerPoint explaining what an exact differential was, right?
Mm,
It's a first and second derivative done in both directions.
Okay, yeah, I got that. I just wanted to make sure I wasn't missing any reading or anything that went with that one, like in the book.
Anything else?
no, that should be good.
So I'm going to save this PowerPoint. And what I have here is, I think I named it updated with text. And so I'm going to change the order of this. Just, we're not done with this. You don't really need all of these different versions. I'll erase some of the versions.
Okay.
I'll call it updated with text. So you can see I have multiple versions as we've gone through this, but so that anything that I've written will be preserved. And I'll move this out to the canvas. Okay, any other questions?
No, thank you, Dr. Correa.
All right, so we have stuff to finish next time in terms of going over the experimental data in those 2 Doherty et al. papers, okay, from the Acres Lab. And we'll revisit some of the same concepts. I'll show you figures from another book that explain this in a slightly different way that hopefully will make it clearer. I realize a lot of this is dense and complicated. Anything else? Okay. So you're working on, some of you are still working on 5. I've basically told you that the last problem, the derivation, basically none of you did anything correctly. So I'm encouraging you to try again. And then now you're working on 6.
6, yeah.
Okay. All right.
Thank
So
you.
next week, we'll finish up the hemoglobin papers. A couple of things that I'll bring in for hopefully clarification or insight. And I think the week after that is spring break. So we'll miss a week and start again on the 22nd or something, I think is when we start again. Okay. So let me stop recording and then I'll go away. See you next week.